So in the previous video, we looked at calculating the built-in potential of the PN junction when it's in thermal equilibrium. And this time we're going to look at a calculation to work out the width of the depletion region when it's also in thermal equilibrium. So we have a formula for this calculation. So W, the depletion region width, is equal to the square root of 2 times epsilon s, which is the permittivity of silicon, over Q, which is the charge of an electron, multiplied by Na, which is our acceptor concentration on the P side of our PN junction, plus Nd, which is the concentration of donor atoms on the N side of our PN junction. That's divided by Na times Nd. Okay, and then that is multiplied by VBI. Now, in the previous video, we have calculated VBI. So we have previously calculated, now obviously this is for this example with these doping concentrations, VBI, and if I look, that was equal to 0.634 volts. Okay, now what I would like to do here before we go on with this is just to plug in some of the values that we have used from the previous example, right? So in this example we said that Na was equal to 1 by 10 to the 15 atoms per centimeter cubed, and that Nd was equal to 1 by 10 to the power of 16 atoms per centimeter cubed. Now, the other thing that's in this equation that maybe we haven't come across before is epsilon s, which is the permittivity of silicon. So the permittivity is basically the measurement of how well an electric field can be built across the material. You may have come across this before when you were looking at calculating the capacitance of a parallel plate capacitor. All right, now, seldom will you see the permittivity directly given for material. It's generally given in something that's called the relative permittivity. So it's related back to what is the permittivity of free space or the permittivity of a vacuum, which is a constant value. Okay, so we'll clarify, just sometimes this can cause a little bit of confusion for people, and I feel that it's maybe not as complicated as people think sometimes. But in this case, epsilon s, this is basically the permittivity of silicon. Now, that can be written a different way, right? So, epsilon s, the permittivity of silicon, that can be put down as equal to epsilon 0 multiplied by epsilon, the relative permittivity of silicon. Okay, so in this case, epsilon 0, which is permittivity of free space or a vacuum. So free space, which is a vacuum, and this is a constant, essentially, all right? And then the other thing in this, then, we have, if I can get the camera to focus, is we have the relative permittivity of silicon. Now, what does that mean? This epsilon 0, the permittivity of free space, this is equal to 8.85 by 10 to the power of minus 14 farads per centimeter. So this is the permittivity of free space. The relative permittivity of silicon is equal to 11.7. All right. So what does that mean? Now, what we can then say is that the permittivity of silicon is equal to epsilon 0, or as we've previously said, multiplied by epsilon, the relative permittivity of silicon. And that is equal to 8.85 by 10 to the power of minus 14 farads per centimeter multiplied by 11.7, and that works out to be 1.035 by 10 to the power of minus 12 farads per centimeter. Okay, now what does that mean? That means that the fact that silicon has a relative permittivity of 11.7, that means if you were to build a parallel plate capacitor and in between the plates of your capacitor you had a vacuum or free space, you would get a certain value of capacitance. But if you were to build an identical capacitor except between the two plates, as your dielectric material you had silicon, what you would find is that theoretically the capacitance value that you get for that device would be 11.7 times higher. It just means that you build a better electric field across silicon than you would across the vacuum. All right, now just to simplify things going forward, underneath this in the equation we have Q, which is the charge of electron, which is generally given in coulombs, and you'll see that for the permittivity we have this given in farads per centimeter. So just to simplify this calculation before we go on, I'm going to convert this into a value in coulombs. Alright, so a farad is equal to a coulomb per volt, so therefore epsilon S is equal to 1.035 by 10 to the power of minus 12 what is going to be coulombs per volt centimeters. Alright, so it's just the same number given in coulombs rather than farads. Alright, so I think we have all those values established now, so we're pretty much ready to put them into the equation that we have above. So let's work out the depletion region width. Okay, so W is equal to the square root of 2 times 1.035 by 10 to the power minus 12 coulombs for volt cm over 1.6 by 10 to the power minus 19 coulombs multiplied by, so we have above the line here Na plus Nd, so 1 by 10 to the power of 15 plus 1 by 10 to the power of 16. So you have 1.1 by 10 to the power of 16 atoms per centimeter cubed. Under the line you have Na multiplied by Nd, which is 1 multiplied by 10 to the power of 31 by centimeters to the power of minus 6. And then that is multiplied by VBI, which we previously calculated to be 0.634 volts. Okay. Now, what can we do here? Okay, so we are going to work out a little bit of the numbers here. These guys will cancel, and what you end up with here is 1.29375 by 10 to the power of 7 volts per centimeter. And that is multiplied by 1.1 by 10 to the power of minus 15 per centimeter cubed. Sorry, these should be minus 1 and minus 1. And that is multiplied by 0.634 volts. Alright, this will cancel with this. And then when you work this out, you will get square root of 0.9 by 10 to the power of minus 8 centimeters squared. Alright, and that is equal to 9.49 by 10 to the power of minus 5 centimeters. Now, we're going to put this into more units that are more typical for sort of solid state devices, so the likes of microns or nanometers. Personally, if I'm going to do this, I prefer to put it into millimeters or something like that first, which is what I'm going to do. So 9.49 by 10 to the minus 5 centimeters, that's equal to 9.49 by 10 to the power of minus 4 millimeters. And the reason I do that is then it's just a factor of 10 to the 3 to put it into microns. So it's 9.49 by 10 to the minus 1 microns, and that's equal to 0.949 microns. So what have we calculated there? What that's saying is that if we have built a PN junction on silicon with doping concentrations on the P side of 1 by 10 to the 15 and 1 by 10 to the 16 on the N-type side of the junction, that there should be a depletion region within thermal equilibrium of 0.949 microns in width.